Hello, everyone. My name is Carrie Moosman with the News Center. I'd like to welcome you to today's webinar, The Value of Demonstration Projects, a case study at MnRoad. We are glad you could join in. A video recording of the PDF and the PDF of the presentation you are about to see will be uploaded to the new website, newconcrete.org, following today's webinar. Attendees are in listen-only mode. We will have a brief questionnaire and answer period at the end of the webinar. Please enter your questions at the Q&A. The ideas expressed in the following presentation are those of the speaker and do not necessarily reflect the views of the News Center, ACI, or its committees. As with all concrete mixtures, trial batches should be performed to verify concrete properties. Results may vary due to a variety of circumstances, including temperature and mixture components, among other things. You should consult your materials, cement, and concrete professionals for assistance regarding concrete production or placement. Nothing contained here shall be considered or construed as a warranty or guarantee, either expressed or implied, including any warranty of fitness for a particular purpose. To move to an overview of the presentation appears on the screen. It's also listed on the news website. And now let me tell you about today's speaker. Lawrence Sutter, Ph.D. PE, is a principal of Sutter Engineering LLC. He's also professor emeritus and research professor in materials science and engineering at Michigan Technological University. His focus is concrete durability, the use of supplementary cementitious materials, the advancement of alternative cements and SEMs, and carbon reduction in concrete. He is a fellow of the American Concrete Institute and chairman of Committee 321, Concrete Durability Code, vice chairman of ACI Committee 232, Fly Ash, and secretary of ACI Committee 201, Concrete Durability. He is president of the board for the ACI Center of Excellence for Carbon Neutral Concrete. He is also a fellow of ASTM and a member of committees CO1, Cement, and CO9, Concrete, serving as vice chair of Committee CO9 and chairman of subcommittees CO1.14, non-hydraulic cements, and CO9.24 on supplementary cementitious materials. He is a registered professional engineer in Michigan. And now I present to you Larry Sutter.
Well, thank you for the introduction and welcome everybody. I am presenting here on some work that happened last year at the MnRoad test facility in Minnesota, and I'll give you more information about that in a moment. This presentation was originally presented at the San Francisco conference, and we're replaying it here by popular demand. So where is the industry going? That's where we need to start thinking. I think when we start thinking about this issue of carbon reduction, everyone's thinking about carbon reduction, sustainability, carbon neutral by 2050. Everybody's heard it. And there's always going to be people who want to know, why are we doing this? What's driving this? And so I always fall back on this old Stephen Stills song, there's something happening here and it ain't just exactly clear. And we can argue over if it's happening, if it's not happening. And a lot of people do want to argue over it. I don't really want to argue over it, but you hear things about how tornadoes are no more common than ever. It's just that they're being hyped, and news crews jump on it and they send out cameras and make a big deal of it. And yeah, I'll be happy to admit the news crews do exaggerate on a regular basis. There's this famous one where the guy's pretending to be blown over while two people just walk along nonchalantly in the background. So yeah, that's true. But when you start looking at the data down in the lower right-hand corner, number of tornadoes over the past 3 or 4 decades has increased significantly. Fires, we're all living with fires. We're hearing about fires everywhere. Canada, it seems like half of Canada is burning now. Washington is burning. And yeah, we can argue that maybe it's just bad forestry practices and other things that are leading to this, but it's happening. Something is causing this to happen. This is one set of data that I like. When people talk about, well, the hurricanes are no worse than ever. Well, maybe not. But if you start looking at the number of storms, what this data is showing, the number of cumulative storms with $1 billion damage or more, and look at those, the average, and then look at the more recent years, how many of these major storms we've had. And we just saw another weird one with the storm hitting California. It hasn't happened in 84 years. So I think it's fair to say there's something happening here, and what it is ain't exactly clear. And we can all have theories, we can all argue, but at the end of the day, it comes down to the concrete business. And I would just encourage you to choose wisely when you start thinking about this, because your competitors are in this game as well. Architects, engineers are turning to low carbon materials, or even those that are perceived to be low carbon. And it's not just in vertical construction, it's in infrastructure construction. Concrete has a bullseye in its back, and we all know the story. 7% of the anthropogenic CO2 in the world comes from the production of cement and concrete. It's about 1% in the United States, a little bit less than 1%. But nonetheless, we have the attention of the world, and we need to bring our carbon footprint down. Low carbon, for this to happen, for carbon reduction to occur, it's going to be driven by demand. At the end of the day, it's going to be companies who are asking for it and are willing to go the extra mile, whatever it might be, whether it's in schedule or in cost, to get to that point of carbon reduction. Many private companies are looking at 2035. They're not looking at 2050. And they're looking at broad strategies to reduce their carbon footprint, and the concrete is part of it. We look at companies like Google, Meta, Target, Amazon. They have these data centers, they have other facilities where they have large carbon footprints, and they want to get concrete down to zero, certainly net zero, hopefully zero, so they can use it to offset other carbons so that they can't necessarily get to zero. So they're looking for those strategies. There's going to be policies that are going to drive this. Federal government and state and local agencies are requesting reduced carbon concrete. ACI is developing a code for low carbon concrete. A number of municipalities already have done this. Classes are being set, carbon limits are being set for different classes of concrete. We're tracking carbon footprint by the use of EPDs. That's going to start becoming a commonality in everything that we do. And the other thing to keep in mind is that we're not in this alone. There's several different NGOs and other stakeholders who are working with elected officials to move this needle. So if we as an industry don't do it on their own, someone is going to force us into doing it, and we may not like the solution that they force us into. So how do we do it? What's the path forward for concrete? Well, for concrete pavements anyway, it's certainly going to be less clinker and cement, less cement and concrete, less concrete and construction. That's the mantra. So what does that mean? Well, first we're going to replace clinker content in cement. We're going to do that by using blended cements, whether it's 1L or it's 1P, if it's 1T. We need to start getting into quaternary blends, but we need to get the clinker factor down in our cementitious fraction. And we're going to do it by replacing it with other materials, supplementary cementitious materials. Using less cement in general. The approach here is really to optimize your concrete mixtures, optimize the aggregate structure, get to the lowest possible cementitious content that you can to still attain the same performance that is required for the structure. There's new things we need to start thinking about. We need to start thinking about optimizing how we design, and we need to start thinking about using new concretes to allow us to do that. You look at something like ultra high performance concrete. Here's two different structures that were built, have the same physical properties. The difference is the one on the right was built with UHPC. Now, ultra high performance concrete, UHPC, has a very high cement content. It's got, on average, maybe 1,200 pounds of cement per cubic yard. But the difference is that you only need to use a quarter of the cement. And so the net result of this is you end up reducing your cementitious content in the whole section by a significant fraction. So we need to start thinking about this. And this is really I think one of the most unexplored areas is how to start optimizing our designs, thinking about how we're using concrete, not just putting extra concrete in there for the sake of it, but thinking about it and minimizing it and doing efficient designs. And of course, the thing that we hear a lot about is alternative SCMs, alternative cements. And you have to ask yourself, why are we talking about alternative materials? Well, first of all, you have to realize that alternative materials are not the only solution. Portland cement is here to stay. It's hard to envision it going away, and it's just hard to envision it going away, period. It has a lot of properties that we just simply can't replace with any other material. But in some applications, alternative materials can serve the same purpose with a much lower carbon footprint. And in some cases, they can perform much better than Portland cement can. So that is one of the driving forces, is the performance and the lower carbon footprint. And the other thing that's driving it is the conventional materials that we're used to working with, fly ash and slag, are in limited supply. Fly ash, we're starting to turn the corner maybe with seeing more harvested ash, so we'll have to see how that comes in terms of helping the supply. Slag is basically a finite resource. It's there, we're using it, but we don't have reserves of slag that we can fall into and keep increasing the use of. But we still obviously need to keep using slag at the rate we're using it, if not higher. So in the end, what limits us from going down these roads of doing these different things, of trying these lower clinker cements, of optimizing our gradation, taking out some of the cement, of trying a new material, trying a new design, all the things, what holds us back from doing all these things is risk. There's a risk in it. There's an economic risk, and there's obviously a risk of performance. The risk of performance is something that we are not ever going to compromise on. We're not going to ever cut corners. It's going to cause a life safety issue. Economic issues are something else. We're going to have to start thinking about this in terms of the infamous triple bottom line, start balancing costs and time and schedule against other factors such as carbon reduction. So risk is really at the heart of it. And the way we start to mitigate risk is by demonstrating performance and demonstrating how these materials work and how we can work with them and just get a feel for them. And that's where MnRoad comes in. MnRoad is a facility. It's in the northwest corner of the Twin Cities area, slightly outside of the metropolitan area. And it's really one of the crown jewels of the transportation research infrastructure in this country. It allows us to go in and on this upper section here labeled the westbound I-94 MnRoad mainline. On that section, we can go in and put in whatever types of designs or materials we'd like to try. And then the way it works is once the construction is completed, traffic from westbound I-94 can be routed onto that main line. And so this traffic or these test cells are seeing I-94 traffic, interstate traffic, full trucks, cars, the whole thing, 24/7, all seasons, winter, summer, spring, seeing it all. We have weigh in motion, so we know what kind of loads they're seeing, and all of the different cells are instrumented so we can monitor various properties and track them. If we need to do maintenance on it, we simply close the gate, put the traffic back on westbound I-94, and do whatever maintenance is necessary on the main line section until we have it ready to go and can reopen it. And they also have this other loop called the low volume road where we can do other types of testing where we don't see interstate traffic, but they have a truck running on a regular basis with a fixed load. So it's really an excellent opportunity to test materials in a real world condition. So it's about 3.5 miles long. The research that's done there is sponsored by the National Road Research Alliance, which is 11 different states, 50 industries and associations, and various academic institutions involved. You can see the states that are involved shaded there in the map. And it gives us, as I said, this opportunity to test technologies in a real world environment. So MnDOT contracted with myself and NCE Engineering to help structure and execute the experiment. So we helped them by identifying the material providers, establishing mixture requirements, managing the trial batching, and then coordinating the logistics, which really was at times a cat herding exercise, and structuring a testing program to support the desired research that's going to come out of it. 3 research projects were let, and they were shown here, and in the italics, the company or institution that got that project is listed. So one's looking at the use of carbon dioxide in pavements, one is looking at alternative SCMs, one is looking at alternative cements. So as we started going through the matrix and figuring out what it is that we wanted to look at, what type of materials we wanted to work with, of course, the first thing we thought about was harvested ash. This comes from landfills and ponds. It's typically going to be a mixture of fly ash and bottom ash. And we decided in the end not to use a harvested ash source because harvested ash is becoming more mainstream. And we felt that it was going to be other places where it was going to be tested that, or be used rather, that we'd be better off using this limited amount of space that we had for materials that weren't necessarily making their way into the market. So next thing on our list was ground glass pozzolan. Many of you are familiar with this as ground container glass. We recently passed a standard at ASTM CAT66 for this material. So we did want to have a ground glass pozzolan in the study. There's a number of different manufactured SCMs, and we wanted to have those in the study as well. And we'll talk a little bit more about each of those in a moment. We wanted to look at some different cements. We started out thinking we really wanted to look at LC3. Many of you have heard about LC3. It's a family of cements where rather than having Portland cement clinker and gypsum in the powder, it is well, it can be done with either just a replacement of calcined clay, like shown here, a 30% replacement of calcined clay, or some combination of calcined clay and ground limestone to get the clinker factor down even lower. So that was something we were going to try to get into the study. It turns out we weren't able to get the LC350, but we were able to get a calcined clay into the study. We wanted to look at alkali activated materials, either an alkali activated hydraulic cements or alkali activated non-hydraulic cements, or what's commonly referred to as geopolymers. And we tried to bring in a couple of different producers, but for one reason or another, it just didn't materialize, and we weren't able to bring those into the study. And part of the reason was we had some general requirements that anything had to meet coming in. We first said that, which didn't affect these other materials, but we said if it's an SCM, for example, and you're using Portland cement in the mixture, it has to be a type 1L10. And we set this requirement before the recent shift to 1L cement. So we did it thinking that 1L cements were coming, and I don't know if we were clairvoyant or if we were a catalyst, but for one reason or the other, the 1L10 became very popular shortly after we started going down this road. We said all the mixes had to meet the AASHTO R101 performance engineered concrete requirements. Again, that's a guideline for developing performance engineered mixtures. The only requirements that we specify were 500 psi flexural strength at 28 days and 5 to 8% air, but we did require all the other tests, such as the box test and those types of things to be done, and that information provided. And the real kicker was we said that all these various mixtures had to be batched and mixed at a central batch plant, and they had to be paved using conventional slip form paving equipment. We had some manufacturers that wanted to use volumetric mixers on a job site. Some wanted to form rather than slip form pave, and we just said, no, we're just going to do it the way we would do a pavement. This is going to be a real world test. And so everything had to fall through that particular those particular requirements, and that did eliminate some materials from the matrix. So in the end, we ended up with 16 test cells. 2 of them are control cells. I'll talk about that in a moment. One was an optimized mixture based on the control mixture. We had 3 cells where we were testing the carbon cure technology, 7 cells using, I'm sorry, that's a misprint. It should be 8 cells looking at various types of SCMs, and 2 that were looking at alternative cements. So the control mixture was a standard Minnesota DOT paving mixture, 570 pounds per cubic yard, 30% Class F ash. Typically Coal Creek is what they use, so that's what we use in this particular, these mixtures. A water to cement ratio, cementitious ratio of 0.4 was specified for the control mix. There was no water to cement ratio specified for the other mixes. The control mixtures, we had to have 2 control mixtures because we had to get the carbon cure mixtures from one ready mix producer, and then all the other mixtures came from a second ready mix producer. And so just to have full control of the experiment, we had to have 2 controls. So we had a separate control for the carbon cure, but that was also kind of an interesting part of the study, is it gave us basically the same mix, the control mix, produced from 2 different ready mix producers, and allowed us to just kind of compare how those 2 mixtures compared to each other once finally delivered. The optimized mix was prepared by Iowa State University, and they got it down to 501 pounds per cubic yard total cementitious. Again, still had 30% Coal Creek Class F ash. So again, they took the 570-pound mix, and just through optimization of the aggregate structure, they were able to get it down to near 500 pounds per cubic yard total cementitious. So that's a significant reduction in cementitious content. For the carbon cure study, which is really kind of a separate study from the other ones, as you saw, we had 3 different research experiments. We had, of course, the control. Then we had one mixture that was designed by Carbon Cure with CO2 injection. They used 558 pounds per cubic yard total cementitious with a 30% Coal Creek Class F ash, and then the CO2 injection, of course. And then the second mixture we made was the exact same mixture as I just described, but we did not put in the CO2 injection. And then the third mixture that we did was taking the standard Minnesota DOT control mixture and injecting the CO2 into that mixture. In terms of alternative SCMs, we had carbon upcycling. This is the fly ashes process by grinding in a pressurized carbon-rich environment. It ends up carbonating phases in the material. And so you get embedded carbon. And then you also get size reduction from the grinding process. The net result of their mix design was they came in with 500 pounds per cubic yard and total cementitious 30% ash replacement using their treated ash. Urban Mining was the ground glass provider, and they used the standard 570 mix with a 30% replacement. Terra CO2, and again, I'll talk about these manufactured SCMs in a little more detail in a moment. Terra CO2 is a manufactured SCM, kind of an artificial fly ash, and they came in at 570 total cementitious, but they went to 35% on the SCM replacement. Carbon Limit, again, another SCM, 570 and 30 was their mix design. Their material is a proprietary material included with ground limestone and unnatural pozzolan. S pumice is just a straight pumice-based natural pozzolan, meaning ASTM C618, and they went with the standard 570 mix with a 30% replacement. 3M has a byproduct from their shingle production process, and they ended up mixing that with a Class F ash, so they made a ternary mix. Again, 570 total, 15% of their material, 15% Class F. And Burgess Pigments produces a metakaolin. Many of you are familiar with that, I'm sure. And they came in at 570 total cementitious, 12% of their metakaolin and 18% Coal Creek Class F as a replacement. In terms of the alternative cements, again, we had the Ash Grove, which was basically a 1P30. So it's really a blended cement with 30% calcined clay as the SCM pozzolan replacement. 570 was the total cementitious. Continental Cement made a very interesting mixture for us. They went to what we call the 1L20. Of course, there is no such thing as a 1L20, but that's what we called it. It was 20%, so basically a type 1L cement, but they went to 20% limestone and then went with 30% Class F ash for 570 pounds total cementitious. So this was truly a 50% clinker mix, which was really kind of interesting. And last, we had ultra high materials. This is a proprietary blend. It has 0 Portland cement clinker in the mix. It is an 1157 qualifying cement. Their mixture design used 650 pounds per cubic yard total cementitious. So just a little more detail on some of these alternative FCMs. The carbon upcycling is a patented technology. And again, as they use a ball milling process, and the mill is pressurized with CO2. So they get the size reduction, but the CO2 carbonates calcium rich phases in the ash. So that embeds carbon into the material and gets embedded into the concrete. They state that the process will work with a number of different materials. In this particular case, we just tried it with the fly ash. Terra CO2 is a very interesting company. They're producing a synthetic, what I call a synthetic fly ash. They're basically taking silicate rock with a composition similar to a Class F ash, and then they go through a process of partially melting and cooling this in an airstream to form spherical glass particles that resemble fly ash. The composition, the structure, the morphology all look like a Class F ash. And if you look at their material, this is from their webpage. You can see on the left the feedstock very angular, and then once it goes through the process of being melted and then cooled, you end up with something that looks remarkably similar to a fly ash. And their one of their plans is really to capitalize on transportation costs by lowering transportation costs, I should say. By having these footprints, the plants will have a fairly small footprint and can be located near where it's being used, and so the transportation costs from the source to the job site will be minimized. So it'll be one more way of reducing the carbon footprint of the material. Carbon limit, as I said, has a non-calcined mineral admixture that has a catalyst in it that increases CO2 uptake. So basically it uses it as an SCM and it performs like an SCM, but then once the concrete is hardened, it is going to have a higher rate of CO2 uptake than Portland cement concrete. And again, ultra high materials, a very proprietary blend of materials. So they have 2 different formulations. One is a hydraulic cement, that's the one we use. And they also have a geopolymer formulation, and they are capable of very high strength. It really is a material is probably designed more for structural uses, but very high compressive strength available for this material. One of our challenges with this material is trying to get the strength down into the range where we'd want it for a paving material. And again, just want to talk about the LC3. We were not able to get LC3 into the pure or an LC350, for example, into the study, but we're hoping in future studies we can. But we were able to use the PPC30 as shown here, which is basically as I said earlier, it's a C595 1P30, so 30% pozzolan. The difference is that the pozzolan here, unlike typically what you see with 1Ps is fly ash, in this case it's calcined clay, which is a material that's very interesting. Probably many of you have seen presentations on this, and it's very interesting, number one, because of its performance seems to be quite good, but number two, it has reserves of materials worldwide that actually put it into the realm of being able to supplant a significant fraction of the Portland cement. There is enough material out there, enough clay that can be calcined, that this is a realistic possibility. Again, coming back to the Continental 1L20, if you're not familiar with the 595 specification, it does, the type 1L cement does not allow for more than 15% by mass Portland ground limestone. this is something we need to think about at ASTM and think about how do we move this up a little bit higher. And I think one of the interesting things about this 1L20, as we call it, is the performance that we got indicates that we're really not necessarily walking that close to the edge by going to 20%. It performed really quite well. So the research teams have been selected, the data is being gathered, we got 1 year in, we got 2 more years before the reports will be issued. So we're going to be monitoring these payments over basically three winters, 3 seasons. And then we'll be able to report on the performance. There will be some sort of a life cycle analysis performed, but in most cases, an EPD will not be able to be issued at this point because most of these materials don't have an EPD, and there really isn't a PCR to develop an EPD for many of these. So this is one of the issues that we have to work on, is being able to get EPDs for these emerging materials, get those developed. So some preliminary results from the study I can show you. This is all from samples that were made on construction day. So they're field samples. So you have to take that into account. They're not ideal laboratory conditions. We all know the trials and tribulations of field testing. Sometimes you win, sometimes you lose. But just keep in mind these are all field testing. The other thing to keep in mind when you're looking at this data is that really none of these mixtures were optimized for paving. Every one of these mixtures, if we'd spent a little bit more time with it and really optimized it for paving, we would have seen a much different performance, I think, and much better performance. And that's not to say that what I'm going to show you is bad. What I'm trying to say is that when you say something, you say, well, maybe it could have been a little higher. And the answer is, yeah, maybe it could have. And more than likely, it's because of the lack of optimization that we did in the study. So anyway, these are the control samples. So what we have here in black diamond is the carbon cure control. And then in red is the study control. So remember, we had 2 different ready mix producers. So basically the black and the red are the exact same mixture produced by 2 different ready mix producers that are, probably less than 10 miles apart. The blue is the optimized mix. So that's basically taking the control mixture and taking out roughly 70 pounds of cement. So you can see how the optimized mixture compares to the control. So I think that's the first major takeaway, is that when we start talking about carbon reduction, just removing cement from the mixture and optimizing the mix can get us a long ways towards our goals. And it's really the lowest of the lowest hanging fruit. We really need to be doing this at every possible turn. We put the carbon cure mixes on the same plot, so they're in green. So again, CC/W means carbon cure mix with the carbon cure additive. /W0 means the carbon cure mix without the additive. And the black line, CC control/W, is the control mix with the carbon cure. I'm sorry, that's the carbon control mix with the carbon cure added. And of course, the diamond you already saw, that was a control mix. So we see a slight increase in strength, especially at 28 days. At later days, we're seeing a little bit of a drop off. But again, these are field prepared samples. I think you have to kind of take it with a grain of salt. I think the 28-day data really is probably the best indicator of what the real performance is like. The natural pozzolan mixes are shown here. So on all these plots, I'm going to show you the optimized and the study control. The blue circle and the red circle will be on all these. The blue is optimized, the red is study control. So because I want you just to keep in your head, A, what the controls were, but also B, what did the optimized mix do? Again, the optimized mix, we just simply took out 70 pounds of cementitious material. And so we have the 3 natural pozzolans here, and they're all respectable. They're all in the same ballpark, basically, in terms of compressive strength. We go to the other various cements. We have the 1L20, you have the 1P30, and the ultra high. You can see the ultra high where it gets its name. It definitely has a much higher strength. And again, as I said, one of our challenges is trying to get the strength down on that mixture. The Continental 1L20 is a dotted black line, and you can see it really performed quite well. It's outperforming the controls, that's, you know, you have to, again, this is a different claker. You have to take all these things into account, you know, but nonetheless, at the very minimum, you can say that it's in the same ballpark as the controls. When we look at the alternative SCMs, they're all grouped pretty well. Again, the red circle is the control mix. So most of them are above the control in strength. We had TerraCO2 that was running a little bit lower, but also remember they went with a higher replacement. They went with a 35% replacement. But all are very respectable. Flex rail strength, again, the controls, we had a little bit of weirdness in our flex rail strength data coming from the field. You can see how the carbon cure control kind of went a little bit wonky, but I think probably it's tracking pretty well with the other ones. I think that last one of those two data points, probably the middle data point, is probably throwing us off. And then we throw on the carbon cure mixes, and again, you can see there where they're falling a little bit higher above the controls. And then we go to the natural pozzolan mixes. The Burgess pigments was slightly above the control and it dropped off near the end. And then the Hess pumice and 3M were tracking pretty closely with the controls. And flex strength here, and you can see that these are the various alternative cements. Again, the Continental is the gray line, black circles, performing very well compared to the controls. Ultra high, we had issues with consolidation of the mix, and so these samples just were not properly prepared, and so this data is just not indicative really of its performance. The alternative SCMs, again, controls are the red circle. Most of them are above slightly. TerraCO2 running a little bit below, but again, they had the higher replacement, but all of them are meeting the specification limit of 500. Resistivity, this is kind of an interesting one. Again, we look at the control mixtures and how they all compare to each other. We can throw the carbon cure mixes on there, and they group very tightly around the carbon cure control. And then we can look at the natural pozzolan mixes, and it looks like I got a wrong slide in there. That's the wrong data. Apologize for that. And then the other cements, again, all tracking very closely with the control. When we get to the alternative SCMs, we see some what would, you know, on first appearance, you look at the urban mining, the glass and the carbon limit, you look at the high resistivity, and I think that in fact part of that is true, but I also think part of it might be that this is field data that wasn't corrected for the pore water chemistry, pore fluid chemistry, which can affect the resistivity measurements. So as part of the laboratory studies, this is being looked at again, but there was nothing in there that was certainly bad. It's just, I'm not sure that the two that look very, very good are as good as they are, but I'm sure they're going to plot in above the control or at the control. And then RCPT shown here. And so on the left, red is the study control, blue is the optimized. And the two greens are the carbon, all the greens are all the carbon cure. So the two greens are the carbon cure mixes, the control first, and then with the carbon cure mix with. And then the two after that are the carbon cure mixes without, and then the Okay, I said that backwards. Start over again. The first green one is the carbon cure control. The second green one is the carbon cure control with these with CO2 additive. Then the green bars are the carbon cure mix without the additive, and then the carbon cure mix with the additive. Burgess pigments, pretty significant drop in permeability there, and we all know metakaolin is known for its ability to reduce that permeability. The two natural positons are next, Hess pumice and 3M, followed by the Ash Grove 1P30 in the solid yellow. The Continental 20, again, coming in at very reasonable level of RCPT, and then the ultra high material coming in very, very low. It's very impermeable mixtures that come from that cement. And then the last ones are the alternative FCMs, carbon limit, carbon upcycling, Terra CO2, and the last is the glass urban mining. So closing thoughts, the MnRoad demonstration project is really a critical step. This idea of being able to demonstrate performance is really critical to getting buy-in to using these materials. And MnRoad is just an absolute gem in being able to allow us to do this. This project received very strong support from federal highways, from Minnesota DOT, from the industry that provided all the various materials for this. The construction is completed, performance is being monitored. We're going to be on this for 3 years, so you have to stay tuned for a couple of years. But all the preliminary results are good, and you know, some are performing very good, some are performing good, but there's really nothing out there that we're having heartburn over at this point. And the notable ones I'd like to point out were the 1L20, the carbon upcycling, and the optimized mix. The 1L20, as I said, that was a true 50% clinker mix. And it's performing very, very well. Carbon upcycling, you know, in terms of actual placements, it was probably the nicest looking slab when we got done. It was placed very well, and again, that had 500 pounds of cementitious. So we got down to 500 pounds of cementitious, and it was really probably one of the most workable mixes that we had. And then finally, the optimized mix, 501 pounds per cubic yard of total cementitious. All he did was take the standard MnDOT mix and optimize it. And they have a very, very, very well-performing mixture with a very low carbon footprint. So that is the low-hanging fruit. And these other two that I'm noting here are indications of where we can be going in the future. All the materials, I think, are options for being used in the future, and we're very grateful to have this opportunity to be able to demonstrate them and prove their performance. And so with that, I'd be happy to take any questions that you have, and thank you for your attention.
Thank you, Larry. Does anybody have any questions at this point? I don't see any questions at this point. You can also email questions to us later at info@newconcrete.org. Do you think there are opportunities for other demonstration projects?
Absolutely, particularly in the transportation arena. As part of the IRA funding, the federal highways is going to be supporting additional demonstration projects moving forward. And what that looks like remains to be seen. The program has not been formally announced yet, but it should be formally announced this fall. And I think there's going to be ample opportunity for more demonstrations. On the private sector side, there's also opportunities. You know, as the old joke goes about the private sector compared to academia, that, you know, they expect results. So that's probably the one slight difference here is that, as I said earlier, a lot of these major companies, they're looking at 2035, not 2050, so they want to move. And so when they're doing demo projects, it's not necessarily for the sake of knowledge, although obviously knowledge is involved, but it's really about, can we use this material? And if we can, how do we design with it? How do we move? So I'm actually very interested in trying to get more private sector demos moving, because I think that is going to create a demand, and it's going to create a movement across the whole industry. more so than the public demand, public side, but we need both. We need demos on both sides, and yes, absolutely, there's going to be more coming, absolutely.
Okay,
And there was another question about future research at MnRoad,
Yes.
and the answer is yes. There is going to be some. It's not. I guess I can't speak yet, but there have been proposals submitted. They're being reviewed, and the logistics are being looked at. MnRoad would like to do another set of cells next year. We just need to work through all of the various things that we need to do, not the least of which is funding, but we need to figure it out. But the desire is to do more placements at MnRoad next year. And when going back to the first question, the demonstrations, I think we're going to start seeing demonstration projects nationwide. It's not going to be just MnRoad, it's going to be nationwide. So wherever you're at, I think the opportunities are going to be there.
Okay, well, as I mentioned, you can also email questions to info@newconcrete.org. And our next presentation will be on September 21st at 2:00 Eastern on low carbon concrete technologies, policy, and the pathway to model code language by Matthew Adams, Associate Professor at the New Jersey Institute of Technology. And he's chair of ACI Committee 323, Low Carbon Concrete Code. So we thank you all for joining us today, and a wonderful presentation, Larry. Very good. Please follow us on LinkedIn and Facebook, and track us on our website. We hope that you join us in the future. Thank you.